Calculating standard reaction free energy from standard reduction potentials. So essentially, this is getting us to use the expression. I'm going to have to draw a delta here, a delta G under standard conditions. Where is my thing? Delta G standard equals minus N F, where F is a Faraday constant, and then E for the cell. First of all, we're going to have to work out what our standard cell potential is for this reaction as written. So I'm going to have to work out from here, which is the oxidation reaction, which is the reduction half reaction, and then calculate from the standard reduction potentials what the cell potential is. So here we have chlorine in the -1 oxidation state, nitrogen is 0, hydrogen +1, oxygen -2. I don't think those will be involved in the process. And then we have chlorine 0, N2H4. So if hydrogen is +1, that means nitrogen is -2, hydrogen is +1, and then in hydroxide we got -2 +1. So oxygen and hydrogen, their oxidation states aren't changing. So they are not redoxing. Chlorine is going from -1 to 0. So chlorine is being oxidized. So that is going to be our anode reaction, FYI. And then our nitrogen is going from 0 to -2, so nitrogen is being reduced, so that will be our cathode reaction. In terms of half reaction, then, the nitrogen half reaction is going to match what we see in our ALEKS data tables. So the reduction occurring at the cathode is going to be N2 gas going to N2H4 AQ, and of course we would need to go ahead and balance that. So I think it doesn't tell me, but I can look at the hydroxide there, and I think this is going to be one of those occurring in basic solution. So if I go ahead and balance the hydrogens by adding H plus to the left-hand side, then I'm going to have to add OH minus to both sides, so that will give me water on the left-hand side. So I end up with H2O liquid on the left-hand side and excess hydroxide on the right-hand side, which I think that's going to balance my overall equation that we've been given. That's kind of handy. So that's going to be my reduction half reaction, my reduction potential for that. If I look it up, is going to be minus 1.16 volts. Okay, so there's my standard reduction potential for that one. Okay, and then my other reaction, which is my oxidation half reaction, which is happening at the anode, is going to be my oxidation of chlorine from Cl minus AQ to Cl2 gas. That should be balanced. So then all I have to do is balance mass and balance charge for these guys, because I am going to need to know for my delta G equals minus NF E cell how many electrons are being transferred, which is what that N is. So if I look on this one at the top, it's going to take me 4 electrons to balance here. And on the bottom, it's just going to take me 2 electrons. So I can see that I would have to multiply my oxidation half reaction by 2 in order to get my number of electrons to balance. And I can see that from the actual stoichiometry, right? So I'm going to leave this as is here because I want to actually look up this standard cell potential. So my reduction potential, so this is not for the reaction as written here. My reduction potential is going to be for my reaction written the other way round, which is why I'm leaving the stoichiometry like this for a second, just to make it easier for you to spot if you look it up in the ALEKS data tab. Because remember, standard reduction potentials are only listed written as reductions, right? So if I look this reduction up in my ALEKS data tab, I should get a value for that reduction of 1.358 volts. Okay, so I'm just going to put it out there for a second. So my actual oxidation half reaction that's happening is going to be doubled, right? So times by 2, 4Cl minus AQ goes to 4Cl2, so 2Cl2 gas. Getting ahead of myself here. Um, plus 4 electrons. So now that should be balanced. So I'm trying to do too many things in my head here. So now we are balanced in terms of charge. So when we add this oxidation and reduction half reactions together, the 4 electrons would cancel out. So I know that N equals 4 electrons being transferred in that redox process. Okay, so then to calculate my cell potential, I'm going to do E for the cathode minus E for the anode. And these are going to be the values you take straight from the data tab. Okay, so this is why I have this one written over here for the standard reduction potential. So that will be E for the cathode was minus 1.16 volts and then minus 1.358 volts will give me my standard cell potential for this particular reaction of minus 2.518 volts. Okay, so a little bit of a word to the wise. You might have spotted some things that seem weird, okay? We are looking at this equation as written. Just because the reaction is written like that does not mean it's spontaneous. In fact, you may have already guessed from the standard cell potentials that the normal spontaneous reaction under standard conditions would be that the reaction that's written at the cathode, the reduction of nitrogen, would actually occur in the opposite direction. Look, because it's got a negative reduction potential. So it's much more likely to want to run in reverse as an oxidation. If we look at our oxidation half reaction happening at the anode, right, that reduction potential is big and positive. So it would seem to me the spontaneous reaction would be that chlorine gas would be reduced to chloride, but that is not what we're being asked. So it is very unsurprising to me that I get a negative value for E cell, which would tell me that is non-spontaneous as written. So the reaction as written is non-spontaneous, which means for delta G, we should be expecting to get a positive value of delta G, because remember, a negative value of delta G, our Gibbs free energy, means the reaction as written would be spontaneous, and a positive value of delta G would mean the reaction as written would be non-spontaneous. All right, so my delta G then, I'm going to have to draw another little delta here. Not very good at that. Delta G equals minus NF E cell. And we see that minus sign is going to change the sign of E cell from negative to positive, giving us a positive non-spontaneous delta G. So minus N is 4 moles of electrons times F, the Faraday constant, which is 96,485 in units of coulombs per mole times the standard cell potential that we just calculated, which was minus 2.518 volts. So we are going to see that the moles cancel out and we will get our delta G in units of coulomb volts. We get 9.7180 times 10 to the power of 5 coulomb volts. What is a coulomb volt? I hear you say a CV, not like a Citroen 2CV, the car, right? CV, I believe, is from cheval vapeur, which is horse breaths, so horsepower. 2CV, many horsepower. So anyway, 1 coulomb volt is exactly the same in terms of units as 1 joule. So we can convert coulomb volts into joules. And looking at this very big number, I would be wanting to convert that from joules into kilojoules and give my answer in terms of kilojoules. So I can see that coulomb volts will cancel out and joules will cancel out, and that'll give me an answer of to 3 sig figs, 972 kilojoules. So it's a big positive number. So positive G is non-spontaneous, which absolutely fits with what we saw there.